distant dream. Britain was hungry for coal. As forests disappeared, coal became the fuel of choice for heating homes and powering early industries. But there was a deadly problem. Mines flooded. The deeper miners dug, the more groundwater seeped in. Pumps operated by horses could only go so far. Entire mines were abandoned, flooded tombs of black gold. Britain was sitting on mountains of energy but couldn't reach it. The need was no longer spectacle. It was survival. It was profit. This was also the age of the scientific revolution. Isaac Newton had published his Principia. The Royal Society was formalizing the experimental method. Inventors were no longer lone eccentrics. They were respected, funded, encouraged, and most importantly, Britain had developed patent law. If you invented something valuable, you could protect it and profit from it. The question was no longer, can we harness steam? It was, who will do it first? By 1698, Britain's coal crisis had reached a breaking point. Mines across Cornwall and Newcastle were drowning. Horse-powered pumps were weak, expensive, and broke down constantly. Mine owners were losing fortunes. Someone needed to solve this, or Britain's industrial ambitions would sink into the flooded earth. Enter Thomas Savery, a military engineer and entrepreneur with a bold claim. In 1698, he patented a device he called the miner's friend. It had no moving pistons, no complex mechanics, just a sealed vessel, 2 pipes, and the raw power of steam. Savery's pitch was simple. Steam could do what horses could not. Here's how it worked. Fill a chamber with steam, then spray cold water on the outside. The steam condenses, creating a vacuum that sucks water up from the mine below. Then, blast high-pressure steam into the chamber to force the water up and out. Elegant, simple, revolutionary. Except, it didn't work. Not really. Savery's engine could only lift water about 30 feet, nowhere near deep enough for most mines, and the high-pressure steam? Catastrophic. Boilers exploded, pipes burst, men were scalded. The technology of the era simply couldn't contain the pressure Savery's design demanded. The miner's friend became the miner's nightmare. But Savery had proven one thing. Steam had potential. His patent was broad enough to cover almost any steam-powered water pump, which meant that anyone who wanted to improve on his design would need to work with him, or around him. Enter Thomas Newcomen, an ironmonger from Dartmouth, and his assistant John Calley, a plumber, and glazier. Newcomen wasn't a gentleman scientist. He was a tradesman who understood iron, valves, and practical engineering. He had spent years working with mine owners, hearing their frustrations. He knew Savery's engine failed because it relied on pressure. So Newcomen did the opposite. He built an engine powered by atmospheric pressure and vacuum. The Newcomen engine was a masterpiece of simplicity. A large vertical cylinder held a piston. Steam filled the cylinder from below. Then cold water sprayed inside, condensing the steam instantly. This created a vacuum. The weight of the atmosphere, 14.7 pounds per square inch, pushed the piston down with tremendous force. That motion rocked a massive wooden beam, which pulled up a pump rod from the mine shaft below. In 1712, at a coal mine near Dudley Castle, the first Newcomen engine roared to life. The beam rocked. The pump rod plunged. Water gushed from the flooded mine. For the first time in history, a machine was doing the work of dozens of horses, and it never got tired. Within a decade, Newcomen engines were operating across Britain. By 1733, there were over 100 Newcomen engines in operation. By 1775, that number exceeded 600. The Newcomen engine had saved British mining. By the 1760s, hundreds of these atmospheric giants stood across Cornwall and Newcastle, their massive wooden beams rocking day and night. But there was a problem that gnawed at every mine owner's ledger. The Newcomen engine devoured coal. For every stroke, steam filled the cylinder. Cold water sprayed inside to create vacuum. The piston plunged down. Then came the waste. Before the next stroke, the cylinder had to be reheated from freezing to boiling. Again and again, thousands of times per day. The engine spent more energy heating itself than pumping water. In Cornwall, where coal had to be shipped hundreds of miles, it was devastating. Everyone knew the Newcomen engine was inefficient, but no one knew how to fix it, until a young instrument maker in Glasgow picked up a broken model. Here was a man who measured steam, understood it as a substance with properties that could be quantified. In 1763, the university asked Watt to repair a demonstration model of a Newcomen engine. It was small, barely functional. But when Watt got it working, he noticed something disturbing. The model consumed absurd amounts of steam. He began experimenting obsessively, measuring volumes, calculating steam consumption. The numbers didn't make sense. The cylinder was swallowing 3 to 4 times more steam than it should. Then it hit him. The cold water wasn't just condensing steam, it was freezing the entire cylinder. When fresh steam entered, most of it immediately condensed on the cold metal walls, wasting energy reheating the cylinder instead of pushing the piston. Watt's mind raced back to Joseph Black's lectures. Latent heat. If the cylinder could stay hot, steam wouldn't waste itself. But the vacuum required cold condensation. You couldn't have both in the same space. Or could you? One Sunday afternoon in May 1765, Watt was walking across Glasgow Green, lost in thought. Hot cylinder, cold condensation, same space, impossible. And then, in an instant, the solution arrived. Separate them. Keep the cylinder hot. Condense the steam somewhere else. A separate chamber, connected by a pipe, kept cold and under vacuum. The piston cylinder would never cool. No more thermal waste. Watt hurried back to his workshop and sketched furiously. A cylinder jacketed with steam to maintain constant heat. A separate condenser vessel, cooled externally. The efficiency gains would be enormous. In 1769, he secured a patent, but building it was different than imagining it. He lacked capital and precision metalwork. By 1773, his partner went bankrupt. Watt was in despair. Then Matthew Boulton appeared. Wealthy, ambitious, Boulton owned the Soho manufactory near Birmingham, one of the most advanced metalworking facilities in the world. He bought the patent and brought Watt to Birmingham in 1775. Watt provided genius. Boulton provided capital and salesmanship. When their first commercial engine was installed in 1776, it used 1/3 the coal of a Newcomen engine. In Cornwall, mine owners calculated it would pay for itself in under 2 years through fuel savings alone. Boulton and Watt didn't sell engines. They leased them, taking 1/3 of the coal savings. The more efficient the engine, the more money they made. But Watt wasn't finished. In 1782, he patented the double-acting engine. Steam now drove the piston in both directions. Power doubled without increasing size. Then came rotary motion. Factories needed rotating wheels, not pumping pistons. Watt invented the sun and planet gear system, converting straight-line thrust into smooth rotation. He added the parallel motion linkage to keep the piston perfectly straight, and the centrifugal governor, weighted balls that automatically regulated engine speed. The engine governed itself. By the 1780s, Boulton and Watt engines powered cotton mills in Manchester, ironworks in Birmingham, breweries in London. The rotative engine freed factories from rivers. Industry could exist anywhere coal could be delivered. Cities could industrialize. Production could scale. The efficiency transformation was revolutionary. Newcomen engines converted less than 1% of fuel energy into work. Watt's engines achieved nearly 5%. Fuel costs plummeted, power output soared. By the time Watt retired in 1800, over 500 Boulton and Watt engines operated across Britain and Europe. The unit of power, the Watt, was named in his honor. Watt didn't invent the steam engine, but he perfected it. He took Newcomen's crude pump and transformed it into the power source of the Industrial Revolution. Steam was no longer just a mining tool. It was the heartbeat of a new world. By 1800, steam power had broken free from the mineshaft. Watt's efficient rotary engines were no longer just pumps. They were the universal power source Britain had been waiting for, and they transformed everything. The textile industry exploded first. Cotton mills in Lancashire and Manchester, once dependent on water wheels and the mercy of rivers, now ran on steam. Spinning mules, power looms, carding machines, all driven by Watt's engines running day and night, never stopping, never slowing. Production increased 50-fold in a single generation. British cotton goods flooded global markets, underselling everyone, especially India. For centuries, India had been the world's textile superpower. Indian cotton was legendary, fine, hand-woven, unmatched in quality. The Mughals had perfected the craft over millennia, but steam changed the equation. What took an Indian weaver weeks to produce by hand, a British steam-powered mill could manufacture in hours, and cheaper, much cheaper. Britain imposed tariffs on Indian textiles while forcing India to accept British manufactured goods duty-free. The colonial machine crushed Indian industry systematically. Millions of Indian weavers lost their livelihoods. Villages that had thrived for generations fell into poverty. By 1850, India, once the world's largest economy, had been reduced to a supplier of raw cotton to British mills. The steam engine didn't just power Britain's rise, it engineered India's decline. And Britain got unimaginably rich. The steam engine catalyzed an economic explosion unprecedented in human history. Coal production increased 20-fold between 1750 and 1850. Iron production grew exponentially. Steam-powered blast furnaces, steam-powered rolling mills, steam-powered hammers forging the rails, bridges, and ships of empire. By 1850, Britain produced more than half the world's iron and coal. It controlled global trade routes, dominated manufacturing, and accumulated wealth at staggering scales. The British Empire, powered by steam, became the largest empire the world had ever seen. But steam didn't stop at factories and mines. It began to move. In 1807, an American inventor named Robert Fulton launched the Clermont, the first commercially successful steamboat on the Hudson River. Steam power, once chained to stationary engines, now propelled vessels upstream against currents that had defied oarsmen and sailors for millennia. Rivers became highways. By the 1830s, steamboats dominated American rivers and began crossing the Atlantic. Distance collapsed. Trade accelerated. Then came the ultimate revolution, steam locomotives. In 1804, Richard Trevithick built the first steam-powered railway locomotive in Wales. But it was George Stephenson's rocket in 1829 that proved steam could power not just individual machines, but entire transportation networks. The Stockton and Darlington Railway opened in 1825. The Liverpool and Manchester Railway followed in 1830. Suddenly, goods and people could travel at 30 miles per hour, faster than any horse, any carriage, any human had ever moved on land. Railways exploded across Britain, then Europe, then the world. By 1850, over 6,000 miles of track crisscrossed Britain. Iron rails carried coal from mines, textiles from mills, people from farms to cities. The Industrial Revolution, which had begun in textile mills and coal mines, now moved at the speed of steam across continents. Economies integrated. Cities grew. Time itself was standardized because railways demanded precise schedules. And it all traced back to Hero's spinning toy in Alexandria, to flooded British coal mines, to Savery's dangerous experiments, to Newcomen's rocking beam, and to Watt's brilliant separation of heat and cold. The steam engine didn't just change industry, it changed civilization. It rewired economics, redrew maps, and reset the balance of global power for the next 2 centuries. The age of muscle, wind, and water was over. The age of machines had begun, and at the heart of it all was steam, ancient, patient, waiting for 1,700 years for humanity to finally understand its power and unleash it upon the world. If you enjoyed this journey through the evolution of the steam engine, please subscribe and hit the notification bell so you don't miss our next deep dive into the inventions that shaped history. Drop a comment below. What invention should we cover next? The telegraph, the printing press, the airplane? Let us know, and we'll bring you the full story of how it changed everything.